Now let's pivot a bit and take a look at big O notation. So big O notation is a way to express the worst case running time of an algorithm as a function of its input size, n. Okay, so why is this important? Let's say that I have 10 inputs. Okay, so my n is 10 right now. If I was in linear time, so my algorithm runs in O of n. For simplicity, let's say it takes exactly n operations. We would need 10 operations to complete my algorithm, okay? Now let's say it ran in quadratic time. And let's say it takes exactly n squared operations. We would already be at 100. And then if our algorithm was somehow in exponential time, for simplicity again, let's say it takes exactly 2 to the power of n operations, we would already be at 1,024 operations for 10 inputs. Okay, so this problem only gets bigger the more inputs you have. At n equal to 100, O of n would be 100. O of n squared would be at 10,000. And then O of 2n is at an astronomically big number already. Okay? We're moving, that's 30 decimal places to the right. So it's really important that A, we understand the running time of our algorithms, and B, we try to find the most efficient solution possible. Okay? So here I have the inequalities listed. I also have a handy dandy graph where we can see that constant time, so O of 1 is going to grow slower than logarithmic time, slower than linear time, slower than log linear time, slower than quadratic time, which is slower than cubic time, which is slower than exponential time, which is slower than factorial time. The main ones you need to know are just these first few. You don't really need to know exponential or factorial. So how do we determine big O? Okay. We're just going to count, so we're going to look at our code, we're going to count the number of operations it takes, and we're going to simplify it to its fastest growing term, its dominant term. Okay, so if you can't tell by looking at this, big O notation kind of hides the slower growing terms and constants. For example, if our algorithm, our code, took 2n plus 8 operations, that would just simplify to O of n. Okay? Now, why is this the case? If you think back to your calculus class, if we take the limit as something approaches infinity of x cubed plus x squared plus something, as the number gets bigger and bigger, as we can also see here, the smaller terms start to matter less and less. So essentially, when you're at large enough of a number, the only factor that matters is your dominant term, is that fastest growing term. In this case, it's x cubed. Okay? So almost all of our operations can be done in linear time. So our assignment, assigning 15 to variable x, arithmetic and comparison operations, that sort of thing, they all run in linear time, whereas loops are generally in linear time. We'll see why in a second. And then the only thing that you really have to memorize is that Python's sorting method runs in log linear time, so n log n time. So you have to keep that in mind because it's not as spottable as a loop, for example. Let's see why this is. What are the running times of the following functions? Let's just say that everything that runs in constant time, like our assignments and everything, is exactly one operation. Again, it doesn't really matter because whenever you're calculating big O, you're going to lose all the constants and the smaller terms anyway. So if you miss an assignment or anything, it doesn't really matter. Okay. First, we're going to calculate the length of our list. So we can do that in O of 1 time. So that's one operation, and then we're going to assign it to n. So that's 2 operations here. Okay. And then we have a loop here. The easiest way for me to think of a loop, it may be because I'm a math major, is we're going to do a summation from I equal to 0 to n minus 1. Okay, because we're not going to include n itself. So this is the for loop itself. Okay. And then how many operations is this print? we have an index, a concatenation, and a print, so we'll say it's 3. So each time we run the loop, it's going to take 3 operations. Okay? So what does this equate to? It's going to be when I is equal to 0, we're going to have 3, plus when I equal to 1, we're going to have 3, plus we're going to keep going until we have I equal to n minus 1. And another way of thinking of this repeated addition is just multiplication, right? So 3 times how many times we did it, which is n. So our entire function is going to be 3n plus 2. We're going to drop everything except the dominant term, and we're going to get O of n. Okay, let's do that again for the next function. Let's say this is 2 operations, and then our loop is going to run n times. So we have an n, and let's say this is 3 operations again, because it's 2 indices and a print. And we're just going to multiply that together to get 3n squared. Okay? Okay. Now we can recognize that this inner for loop is the same as the one here. Okay? So it's going to be 3n. And then we're going to loop through that again for our outer for loop. Okay? Because we're going to run this process that takes 3n operations n times. Okay? So this is 3. So when I equal to 0, we're going to get 3n plus I equal to 1, 3n plus 3n. And then this is happening n times. So it's going to be 3n times n times, which is 3n squared. Okay? So the total number of operations is going to be roughly 3n squared plus 2, and that'll just convert to O of n squared in big O notation. Okay? Another example. Now we have while loops. Okay, so we have to see when we no longer meet that condition. So let's figure out what this is doing first. Let's do a small example. Let's do n equal to 10. We're going to set I equal to 1. So while I is less than 10, we're going to double I for the next iteration. Okay? I'm going to print I out. So the first time around, when I is just 1, it's going to print 1, and then we're going to double it, and we're going to print 2, and then we're going to double it, and we're going to print 4, and then we're going to double it, and we're going to print 8. And then the next time we multiply by 2, we'd be at 16, and we would not be able to enter the loop again. Okay? So you can see that each time we're multiplying by 2. Okay? And this was iteration 0, 1, 2, 3. So you can probably see by multiplying by 2 constantly, our I is equal to 2 to the power of k, where k is our iteration. Okay? Okay? Because this is 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 4, or 2 to the power of 3, sorry. So I equals to 2k. And our condition to keep running the loop is I is less than n. So when do we exit the loop? When I is greater than or equal to n. So when 2 to the power of k is greater than or equal to n. And to solve for k, we just take the log base 2 of n. Okay? So k is the number of times we can double I before we reach the stopping condition, which is when I is greater than or equal to n. So if this is 1 operation and this is 2 operations, to do I times 2 and assign it, and this is 1 operation, we would have 1 plus log base 2 of n times, remember this is inside the loop, so it's getting repeated log n times. So 2 plus 1 is 3. So we're going to get 1 plus 3 log n as our as our number of operations, which is just going to simplify down to O of log n. Okay? Now, this time we're going to start with I equal to n. It's going to be equal to 10, and we're going to see how many times we can divide it by 2 before it becomes less than 1, which is our stopping condition. Because if we enter the loop while I is greater than or equal to 1, then we fail to enter when I is less than 1. Okay? Let's see here. We would have 10, and then integer division by 2. We would have 5. Integer division by 2 would be 2. Integer division by 1 would be 1. Okay? And then the next time around would be 0, which would exit our loop because 0 is less than 1. Okay? So to be able to do it 4 times. Now this is the opposite of the first one, where each time we're dividing by 2. Or if you think about it, that's the same as multiplying by a half multiple times. And that's the same over 1 over 2k. Now we started with I equal to n, and we're just trying to see how many iterations we can continue for before that is less than 1. So now let's solve for k with our new equation. If we multiply both sides, we'll end up with almost the same thing as last time. Okay, so we're going to be in logarithmic time once more. Essentially, whenever you see a while loop being multiplied by 2 or being divided by 2, we're going to be in logarithmic time. So let's say this is 1 operation, this is 2 operations, this is 1 operation, so it's 1 plus log 2 of n times 2 plus 1 again, which is 1 plus 3 log n, and that should just simplify to log n once more. Now let's look at this function. We have a list of duplicates and we'll return true if an element appears 2 or more times. Now what's the worst case running time here? It's when we return false, because that means you went through all elements of the list, you went through the entire loop, and you couldn't find a duplicate. Okay? Because if we returned true early, then it could only take a couple operations, but we want to look at the worst possible scenario, and that's when we return false. Okay? As I said before, this is 2 operations, one to calculate this and one to assign. Let's say it takes 1 operation for both index and then 1 for the comparison, so it's going to take 3 operations for this line. This is a conditional statement, so if the condition isn't true, we may run it 0 times or we run it 1 time. Okay? But that's actually separate from the loop, because as soon as you run it, we would exit. Okay? So let's take that out. So we're just going to consider the 3. Same with this, return false. It's going to be 0 or 1. Okay? But only one of these is going to be returned, so in total, this is 1. Okay? Now let's look at this loop. Okay, this loop is going to be from I equal to 0 to n minus 1, right? Because it's a sequence of numbers from 0 to n minus 1, not including n. So this one is going to be n minus 1, I equal to 1. Okay? And each time it's going to be 3 operations, so that's 3 plus so on and so forth, which is going to be n minus 1 times. Okay? So this is 3n minus 1. If we put that into our outer loop, we're going to get 3n minus 1 plus 3n minus 1 plus so on. And that's going to run n times. So you're going to get 3n times n minus 1. Operations. In other words, we're going to get 3n squared minus 3 operations from these loops here. Okay. Just move that over. Let's add our two operations from this line and our one return true or false operation. And that's just going to simplify to O of n squared. Sounds good. Second last one. Now that I feel like we've gotten comfortable with loops being O of n, I'm just going to simplify this to O of n. Okay. This is two operations, so we'll do O of 1. And this one here, sorting a duplicate or sorting a list, remember this takes O n log n. Okay? So right away, O n log n is bigger than our O of n from the loop. So automatically this algorithm is going to be n log n. Just because of this one sort line, it's a little harder to spot because with a loop, you can kind of visualize how many times you're going through it, whereas with a sorting algorithm, although you do learn a bit in class, sorting isn't on the final exam, so I won't be covering it today, but they are n log n. They are n log n algorithms, so you just have to remember that if you see a sort function, make sure you account for that. Okay. Last thing that might trick you up is if I have something like this, where let's say this is one operation, this is one operation, this is two operations, one for the calculation, one for the assignment. How many times is this getting summed up? We're going from 0 to 100, 2, which is going to be 2 plus 2 plus so on, 100 times, 101 times, which is 2 times 101, 202 operations. If we add these two here, that's going to be 204 operations. And notice how none of this is a function of n. Okay? So no matter how big your input is, it's not actually affecting the running time of the algorithm. So this simplifies to O of 1. It's in constant time. But yes, if it's not a function of n, it's linear. Okay. Now let's go on to sets. So a set is another mutable type. It's a collection of objects. We did note it with the curly braces. That is unordered, so we can't index elements, and it has no duplicates. So those are the two main properties of a set. So here I have a set with 3 elements, 10, 1, and 100. Note that if I try to do this, I would get an error because it's unordered, so it doesn't necessarily mean that 10 is the first element, even though it looks that way right now. It's unordered, so we can't index things. Okay. With that, we have a couple of methods as usual. So we have add, which adds an element to the set. Remember, we aren't allowed duplicates, so if that element already exists in the set, nothing happens. Okay? So if we add 100 to my set, notice how there's already 100 in there. So when I ask for my set back, nothing's going to change. And then if I add 1,000, which is not already in my set, it's going to modify the set because a set is mutable. So our set methods are going to modify our original set, and we're going to get my original set with 1,000 added to it. Okay. Similar thinking. We have a remove element function that removes element from the set if it's in there. So here I removed 1 from my set. So now my set looks like 1,000, 10, 100. Okay. So if I ask, is 1 in my set, it's going to return false, okay? Because we modified the original set. You can see that here as well, okay? A nice thing about sets is we can switch between a set and a list to remove duplicate objects, okay? So the set function will convert whatever object we give it into a set, and the list function will turn whatever we give it into a list, okay? I have this list 10, 10, 10, 1,000, 1, 10, 100, okay? When I do the set of that, that's going to remove all the duplicates, okay? Because a set can't have duplicates, so it'll automatically do that for us. And then I can turn it back into a list using the list conversion function. Okay, so then we'll get that right there. Remember, sets are unordered, so my set could have also looked like this, which matches that solution, and then when I turned it into a list, it would have turned into that as well. Okay, next let's move on to dictionaries. These are sets. They just store data in unique key value pairs. So we can index them. We index them with their key. So their key has to be unique, okay? That key can be any immutable type, so strings, numbers, tuples, as long as you cannot change your key, because all of our keys have to be unique so that we can index them consistently, okay? And then our value, just like a list, it can be any type. So here I have an example dictionary. I have key 1 with its value, key 2 with its value, which is a list, okay? So here, if I did my dictionary and I indexed by key 1, I would get value returned to me, okay? So let's take a look at this example. I have a dictionary called task completion, where my key is the name of a task as a string, and then the value is its completion status, so a Boolean. Okay, so here I have my task, study for ITI, and its completion status is true. And then I have my task, subscribe, and its completion status is false. Okay, so that's my dictionary. Remember, sets are mutable, so are dictionaries. So if I index by the key subscribe, I'll get its value, which is false, right? But I can also set that to true. Okay, that'll modify our dictionary for us. So now, if I print out task completion, okay, the key that we indexed, its value is now true. It also supports the in keyword, so I can ask, is join Discord server in task completion? That's asking, is this key in task completion? So if it was, it would look like this. Okay, so we're asking if the key is in the dictionary, not if the value is. Let's take a look at an example. So I have a dictionary of students where their key is their student number, and I have a list with their name and their grade as the value. This is a good example as to why a dictionary can be a lot more powerful than a standard list, because especially here where my keys are integer values, if I wanted to store this information at index 300,200,000, I would have 300,199,999 empty indices before it. Okay, so a key is very powerful in that sense. So these are their student numbers, and then each key's value is a list with their name and their grade. Okay, and then we have a loop here. So for each student number in students, remember, we go through dictionaries based on their keys. And here we have a double index. So students, the first time we iterate through, our student number is going to be the first one. So it's going to be 300, 200,000, right? That's going to give us Perry the platypus. And his grade of 85, okay? Now this is a list. The value of our dictionary at this key is a list, so that can be indexed further. So if we index that, at index 1, we'd be getting 0, 1, we'd be getting their grade. Okay? So this is saying we're going to loop through all the students in our dictionary. If their grade is not none, like this guy, then we're going to go in and we're going to change it. We're going to give them a 5% bump. Okay? So for example, with Perry the platypus, right now is 85, right? Right there. We're just going to add 5, and that's going to become 90. And that's possible because our value is a list, and we can also index and change a list. Okay? So then the next time that you ask for Perry the platypus, you're going to get his name again. And now he's going to have a 90. Okay? So this here is boosting everyone's grade by 5%. And then once we exit the loop, don't think I forgot about you. This is you as a student. We're going to set your grade to 100 because that's what you're going to get on this exam after this final prep. And then we're going to print out students. Okay? So those are our students printed out. You can see that everyone got a 5% bump if their grade was already inputted, and then we gave you 100. Sounds good. Second last topic, this is the big one on the final, because this is a very important aspect of computer science. It's recursion. So that's when a function calls itself until it reaches a base case, okay? So a recursive function is generally going to be in this format here. So it's going to take an input. If we've reached the base case, so that's our stopping condition, we're going to return something or we're not going to call again, that essentially ends the recursive calls. If we haven't reached our base case yet, we're going to call the recursive function again. So we're going to call itself with a new input, okay? And it's going to keep going back and forth until we reach a base case and return something, or just stop calling. Okay, so the key thing here is that input needs to be modified each call, and this base case has to be true eventually so that we don't have infinite recursion going on. We don't want to be in an infinite loop, okay? It's essentially another way to implement a loop, but it's really powerful because it can simplify a lot of things, especially for things like trees that you'll learn next year. And then the height or the depth of recursion is the number of recursive calls. So how many times a function can call itself before we get to the base case. Okay, let's do some examples. So what does the following code print if n equals 5? And what is the height of recursion? Okay. So essentially our main is going to call mystery printer. Our main is going to call mystery printer 5. Okay? That doesn't count as a recursive call. That's how we get into our function. So right now we have n equal to 5. Now that we're in our function, is n equal to 0? No. So we're going to print n, and then we're going to call mystery printer again. Okay? So let's print n. So we're going to print out 5. Okay, and then we're going to call mystery printer 4. Mystery printer n minus 1. Now, if you remember from the functions explanation, whenever we have a function calling, or whenever we had main calling a function, when we call the function, we start it up and then we don't proceed to our code down here until the function is done. Okay, so in this case, even though we don't really have any code under here, mystery printer 5 is still open. It's still waiting for the answer from mystery printer n minus 1. Okay, so we're going to keep going down until we reach the base case. I may run out of space though. When n is 4, n is not equal to 0 yet, so we can't go into that if statement. We'll have to go into else. So we'll print out 4 again, and then we'll call mystery printer n minus 1. So then we'll pass it 3. Now n equals to 3. It still doesn't satisfy that condition, so we'll print out 3, and we'll call mystery printer n minus 1, which is mystery printer 2. I think I'm going to have to go in a little circle. Okay, when n is 2, our condition isn't met yet, so we're going to call mystery printer 1. And that isn't going to satisfy the condition either, so we're going to do one last call to mystery printer 0. Okay, so now that n equals to 0, our condition is satisfied, so we're just going to print lift off. Okay, and we're going to return none in this case, but all of our other functions that called us are waiting for us to return back to them so that they can close as well, because they're all stuck on this line right now. They're all waiting for our function to end. Just like here, we're waiting for our function so we can continue with the rest of the main. All of our previous recursive calls are waiting for us to answer them, essentially. So we're just going to return our none type and just let them know we're done. Okay, so all these are going to close back out. And that's the end of it. So what is the height of recursion here? So we don't count the first call that we made to start the function. We count how many times we called ourselves. So we called ourselves once here, then twice here, 3 times here, the 4th time here, and the 5th time here. So our height of recursion is 5. Okay. Next example, what do the following functions print if n is 10, and what is the height of recursion again? Okay, let's do our countdown first. So we're going to call countdown 10. I'm going to have n equal to 10. Okay, and I'll get my console ready. So in this one, this condition replaces our base case, our if else for our base case. Okay, so essentially, instead of doing this, we've just done if n is greater than 0. So essentially, anytime n is less than or equal to 0, that's our stopping condition. That's our base case. And that's when we don't call anymore. So right now, n is bigger than 0 because n is 10. So we're going to print out 10. And then we're going to call countdown n minus 2. So we're going to call and pass it n minus 2, which is 8. So n is 8 now. That is still bigger than 0, so we haven't reached our base case. We're going to keep going. So we're going to call 6. Still not our base case yet. So we're going to call 4. Here we'll call 2. Not our base case yet. So we're going to call one more time. And now n is 0. So now that we're here, oh, I forgot to print. This will print 8, this will print 6, this will print 4, this will print 2. Okay. Now that we've reached n equal to 0, this condition is no longer satisfied, so we're not going to go in here. Okay. And we're not going to print 0 either because we're not going into the code block. So we're not going to call, we're just going to return nothing back and close out all of the recursive calls that were waiting for us to answer them. Okay. So here, how many times do we have to call ourselves? This is 1, 2, 3, 4, 5 again. Now let's go count up. Very, very similar, except for one switcheroo here. We'll see what that does. Okay. So we're gonna call count up from the main. We're gonna start it. So first things first, n is 10. Okay. Have we reached the base case yet? No, because n is still bigger than 0, so we're gonna run this. Now here, when we did count down, we printed, so I would print 10, and then I'd recursive call. This time, I'm going to recursive call, and then I'm going to print. Okay? So I'm going to wait for it up here. I'm going to call down. I'm going to call count up 8. So we're going to keep going until we reach our base case, which is when n is less than or equal to 0. So we finally reached n equal to 0. So now the base case is satisfied, and this condition is not true, so we're not going to go in here. Okay, so we're just going to go back down. We're not doing anything this time around, so we're going to go back down. And remember, each function is still on this line, waiting for it to end so that it can print, so then it can do this line. Okay, so for example, when we called count up 2, okay, it got to here when we called count up 0, and it waited for this one to finish. Okay, so now this is done, and we can do this line. So we're going to print 2. Okay. Same with 4. 4 was waiting for 2 to finish. It was stuck on this line as well for count up 2. So now it will also get to print 4. Okay. And it just keeps going back like that. Okay. So basically we're finishing off whatever was remaining in the function, aka this line. Anything after the recursive call, we're finishing up now, because as soon as we make a recursive call, as soon as we call a function in general, we have to wait for it to finish and give its value back to us before we can continue with our program. Okay. So lastly, we'll print 10, and that's the end of that. Again, this has a height of 5 because we called 5 times. Okay. Okay. Our next example is a classic recursion example. It's factorials. So if you don't know, n factorial is n times n minus 1 times n minus 2 times so on, which is the same as n times n minus 1 factorial. Okay, so for example, 4 factorial can be written as 4 times 3 times 2 times 1, or we can do 4 times 3 factorial, and then 3 factorial is 3 times 2 factorial, and 2 factorial is 2 times 1 factorial, and 1 factorial is 1 times 0 factorial, and 0 factorial is 1. So that's the thought process here. We're taking n times the factorial of n minus 1. So what does the following code print if n equals to 4, and what is the height of recursion? Remember that the right-hand side of an expression is evaluated before getting assigned to the variable on the left-hand side. So that's referring to this here. When we do n times factorial, we're going to evaluate factorial first and then multiply it by n. And then if we were to save this to any function, and then if we were to save this to any variable, for example, this would have to get run and then it would get put in the variable, okay? So let's call factorial 4 from the main, right? So we're going to have n equal to 4 right now, and we're going to return n times n factorial. So we're going to have to wait for our recursive call to return so that we can figure out what this value is, okay? So let's keep calling until we reach our base case where n equal to 0. Let's call factorial n minus 1, which is factorial 3. Okay. It's going to wait again. It's going to call n equal to 2. Okay, last function call. When n is 0, instead of returning n times factorial, we're just going to return 1. Okay, so we're going to send that return value back and we're going to fill in all the blanks, okay? Because we're waiting for this answer, and right now that answer is 1 for the base case. So we're going to send that back. Okay, so 1 factorial is n times 1, so it's 1 times 1 right now, okay? And that's 1. Okay, so it's 1 times 1. And then n times 1, so 2 times 1 is 2, so we're going to send that back. And we're going to get 2. Okay, and then 3 factorial is 3 times 2, so we're going to get 6. Okay, and then lastly, for factorial 4, it's n times 6, so 4 times 6, we're going to return 24. And then our height of recursion is 1, 2, 3, 4 calls. Okay. Last topic of the day, last topic of the course. I saved this one for last because I felt it wasn't tested as heavily. You also spend a whole course on it in ITI 1121 when you do object-oriented programming in Java. So it's not a big part of the ITI 1120 final. But I do think it's important to know it's a very useful thing. So in object-oriented programming, there's this idea of classes and objects, which can seem a little overwhelming at first, but we've been dealing with classes and objects the entire time. We just haven't really discussed it, okay? So for example, a list is a class, okay? So a class is a blueprint that defines common attributes and methods. So all lists are mutable. They have the notion of indices. They have methods to append or remove, or I guess in this sense, pop. Those are all common to a list. They're what makes a list, okay? And then whenever we define a list, like let's say my list, and we give it values, right? This is an object, okay? So it's a real world instance of that class. It's an actual list in particular. A class is like a list in concept, and then our object is our actual list. We'll go through examples, don't worry. Okay, so how do we create that in Python? So we use the keyword class, and then we input our class name. And then the first thing we're going to have in our class is a constructor. So that's how we make an object of this class. That's how I make a string in particular. That's how I make a list in particular, okay? So every time we define a method in a class, our first parameter is always going to be self. So that's giving it a reference to the object, okay? And then we can have attributes defined. We can set default values to attributes. For example, if you had a rectangle class and you had a length and a width and you want them to default to 0, if the user doesn't give that to you, you can set length equal to 0, width equal to 0. Okay? And then your constructor is going to take the attributes that the user gives you, so that's these attributes here, and self.attribute is the object itself's data. Okay, so we're going to assign it to that. It's very hard to explain when it's theoretical. We'll see examples. And then we can also have methods, either with no parameters, quote unquote. Okay, when you call it, let's say we'll call the class object, it would just look like this. Okay, because self is called automatically. So if it's just self, there's no parameters that the user has to give it, or you can specify with a parameter and ask the user to give you something for your method. Okay, we will look at examples. Aside from init, which is our constructor, it tells you all the attributes of the class. We also have methods string and representation, which return different string representations of our object. So the string method will return the quote-unquote pretty representation of it, so whatever we want it to display when we use it in print. And then the representation function is just going to return whatever we want it to print in shell when we evaluate it. Okay, let's say I have a string. So the class is a string, and then a specific string is an object. It's an instance of the class string. So let's say hello. Okay, if I were to use print s, it would give me hello like this. But if I were to type it in my shell, if I just asked for s, it would give me hello with the quotation marks to indicate that it's a string. Okay, so this one is the string representation, it's the pretty one, and then this is the normal representation. Okay. I just wanted to include that in case it comes up, because I know it was part of a lab before. Okay, and then whenever we want to access an object's attributes or methods, just like we did for string methods and list methods and sets, that sort of thing, we use the dot operator. Okay, s dot operator, okay, it's calling a method from s, okay, from the class of strings. So as I mentioned before on this slide, our class definitions have a reference to self, but when we call it, we don't actually pass the self parameter. So you can see that here I don't pass the self parameter, here I don't pass the self parameter, I just pass it the parameter we named parameter. Here we don't pass self, I just pass it the values that I want. Okay, so this is my first attribute, this is my second attribute. And then if I have my object and I use dot, the dot operator, and I ask it for attribute 1, this is attribute 1. Right back here. That first parameter, excluding self, is attribute 1. So it looks like this right now. This is value 1. And we're setting self.attribute to value 1 from here, okay? So when we do object name dot attribute 1, we're getting value 1 back. Okay, let's look at an example, and I swear it'll be easier from that. Okay, let's look at a person. So a person is a class. They have attributes about them, so they have traits and characteristics you can think of an attribute as. So here we have their first name, their last name, and their age. Okay, so self is the reference to the person, and then we have strings and their age. Okay, so once we receive those parameters from the user about their object, we're going to assign it to the object itself, to the instance. And then we also have a method to introduce themselves. Okay, so here they'll just print, hi, my name is first name, last name. Okay, so let's make a person object. So notice that this is a person. It's an object of class persons. It's a specific person, whereas a person is just like this broad concept of a thing. So right now I have a person, okay? And each person has these parameters here that I'm going to write down, okay? So they have a first name, a last name, and an age, okay? And in my constructor, to create a person, I passed in those variables, okay? So I passed in a first name, I passed in a last name, and I passed in an age, okay? So right now, this is Rachel, this is Q, and this is 20, okay? So we're going to set self.firstname to Rachel, okay? This is my self.firstname, okay? This is referring to the instance. So this is referring to the person, a person in this case. And we're going to set the name to the first name that I provided. Okay, so we're going to set that to Rachel. Okay, same goes for last name. We're going to set our last name to Q. And then we're going to set our age to 20 as an integer. Okay, and that's a person. Okay. Now that I have a person object, which is this little box right here, I can call methods, I can get attributes from it. So if I do a person.age, that's going to a person and it's getting the age. Okay, so we're going to return 20. We can also get the person to introduce themselves because under person, they have a method called introduce self. So I can call, remember we don't pass self, so it's just .introduce. And this will use the attributes of a person, the first name, last name, to introduce themselves. So it'll say, hi, my name is, this should just be self.first name, that should be self.last name. Okay, so it'll look for self.first name, which is here. So it'll get me Rachel. Then we'll add a space, and then we'll look for last name, which is Q. Okay. Oh, period. So that's a person class. Then we also have inheritance. So it's the idea that a class can inherit methods and attributes from their parent class, okay? So to do so, we just add the parent class as a parameter of our class definition, okay? And then if we want to have methods or attributes that were defined in our parent class, we can use this super method, which returns a temporary object of parent so that we can call methods from the parent, okay? So let's say in my parent class, my constructor looks like this. Okay. So as a child class, I would take in everything that the parent has. So I take all of their methods and attributes. So I have a parent parameter, and then I can add on to it, I can overwrite it. So I have my own child parameter as well. But I want to make use of the fact that I already deal with this parent parameter in my parent class. So instead of trying to rewrite everything in parent class, I'm just going to call super, which gives me an object of type parent. And then I just call init and I give it this parent parameter and it'll set it for me, okay? And then I can add on by having my own child parameters. So that allows us to add attributes or methods specific to a child class, such as child parameter, or we can override or extend those of the parent. In this case, we extended the constructor to have parent and child parameter. Okay? We're able to override things because Python will use the attribute or method from the child class first, and then if it doesn't exist or you can't find it, it'll then look in the parent, okay? So we're allowed to overwrite things. for example, if you had a class rectangle with a function area, right? That's calculated by length times width. And then you had a subclass called square, because squares are rectangles, but you wanted to overwrite area so that it's just length times length, because it's the same thing. You can do that because whenever Python looks for an area function, it'll look in the child class first before it goes up. Okay, let's see an example of that with a student. So a student is a person. So a student has all the same attributes that a person does. Okay, they have a first name, they have a last name, they have an age. And then we added some parameters that are specific to a student. So they have a student number and they have an array of grades. Okay. Then they have a method where they call the introduce function from their superclass. They introduce themselves as a person, and then they also add things that are specific to them. So they'll say my student number is blah, blah, blah. Okay. We also have a new method, which is grade, where we can add grades to our array. Okay. So let's make a student right now. So we're going to make a student, and we're going to pass it all these parameters. Here, because we have a default value, I actually don't have to give in a grades array. If I don't give it in, it'll automatically go to the default value. But because none of the other things have default values, I do have to give those to be able to make the object okay. So let's give it a first name, the last name, the age, the student number, and we'll just go with the default grades. Okay? So when that happens, we're going to call super to deal with the name, to deal with the first name, the last name, and the age. So it's going to do this for us. So that's done for us by calling the parent, okay? So I have my first name, my last name, and my age done. This is now a student. So we have the same attributes as parent. We just extend from them, okay? Because a student is a person. Okay, and then we added our student number, and we'll use the default value for grades, which is just an empty array right now. Okay, so that's our student as an object. Okay. Now from that, I can call a student dot introduce. So here, the first line is going to call the parent's introduce function. Okay. And remember, a parent has the same first name, last name, age as a student, because student takes that information from the fact that it's a person. So this will print out, hi, my name is Rachel Q again. Okay. And then we extended it by adding my student number is, and I will say out my student number. So I would print out my student number, $300 million. Okay. So we print both those lines, one's from our parent and then the other one's from us. Okay. We can also add a grade. So let's say a student dot add grade. Let's add 100. Okay. So it's going to do self.grades.append. What does that mean? Okay. Self.grades is going to access this array here. Okay. And then it's going to append the grade that we gave it. So it's going to get that empty list. It's going to append 100 to it. Okay. So now our list of grades is going to be 100. Okay, it's going to get modified. And then the function just returns it to us. So let's say this was a let's say this was a report card. We would get the list 100 back. Okay, so we get all of our grades back. I hope that makes a little more sense. For the final, the big thing is recursion, because you do spend a whole other course on object-oriented programs, so I wouldn't stress too much if you don't understand it right away. It definitely takes a while, but I'm here if you have any questions. Again, please feel free to reach out to me on the Discord. I don't care if it's at 2 a.m. I will probably be up. Don't be shy. Thank you for joining me today. I hope to see you guys again here. It's been such an honor getting to teach you, and I hope you guys had fun learning. I wish you the best of luck on your exams. I know you're gonna do great. You got this. Deep breaths. And I hope to see you again soon. Take care.